Hello, and welcome to the next chapter in our Calculus 2 adventure. What we're going to be talking about in this chapter are parametric and polar equations. So we're going to start with parametric equations, and then we'll get into the polar coordinate system and then into polar equations. Of course, polar equations are another parametric form of equation. And that's why we start with parametric equations in general. So what I want to do now is I'm going to share my screen with you so you can see the notes a little more easily. And then we'll get into defining what is a parametric equation and how does it relate to what we already know for equations. So when we're talking about parametric equations are useful in different kinds of situations, including ones where the equations aren't actually functions. So it could be a curve that curves back on itself, so it doesn't pass the vertical line test. It is a curve, it is a graph, it's just not a function. So parametric equations are really good for graphing those. They're also good for graphing equations or curves that cannot be expressed explicitly in terms of y. In other words, you can't solve for y on one side and have some expression in terms of the independent variable on the other side. It can't be solved explicitly for y. So parametric equations are good for describing those. And that could be something like e to the y equal to the sine of y. Well, there's no way to get those y's together, right? I mean, that's just not going to happen. Let me write down what that would look like. So you have e to the y equals sine of y. If you tried to get to the y that's in the power here, you'd have to take the natural log, but that's going to bury that one. If you try to get to this y, you have to do arc sine, but that's going to bury that one. You can't get the y's together. And another way of expressing this would be in terms of parameters. So we've got this expression here. Now, it could also have the independent variable in it, x, or something like that, but it could also just be something like this. So, or it could be something where y is itself a function of x expressed somewhere else. So we can see that as well. All right. It's also good for equations where it's describing position with respect to time in either 2 or 3 dimensions, which of course is the space in which we live. 2 dimensions means in a flat 2-dimensional space like the XY plane, and 3 dimensions, well, that's the world we live in, right? The XYZ coordinate system. So parametrics are ideal for describing these. So they get used a lot in physics, where we're trying to describe the position of something at different points in time. Because saying that it's at location 3, 1 doesn't tell me when it's at location 3, 1. So by writing it as a parametric equation, I can get more information, which is when it arrives at the coordinate 3, 1. Now, parametric equations get used extensively in Calculus 3. So you want to make sure that you learn them now and get a good handle on them. This is not something you can delete from your data bank because it is going to come back with a vengeance in Calculus 3. Now, let's go ahead and define what a parameter is, because a parameter is what we have in a parametric equation. So the parameter is an independent variable, often represented by t for time or theta for an angle value. And when we have that, then both the x and the y, if we're in 2 dimensions, or x, y, and z, if we're in 3 dimensions, depend on this independent parameter. So x is a function of t and y is a function of t. And if we're in 3 dimensions, z is a function of t or of theta. And that means that both the x and the y become dependent variables because they depend on the independent parameter t. Now, if t is representing time, this is when an object reaches that particular position. But of course, when we graph it in the xy system or the xyz system, and time doesn't show up in that system. So weirdly, while the parameter tells us when it gets there, it doesn't actually show up in the position of the object. And so it doesn't show up in the graph. So in a sense, it's sort of like a dummy variable that helps us determine when it reaches a certain position, but it doesn't show up in the actual position. So when we talk about the orientation of a parametric equation, we have to realize that as the parameter changes value as t or theta vary between some values over some interval, then the x and the y coordinates, or if we're in 3 dimensions, x, y, z, will trace out a path in a particular direction. And if we're looking at 2 dimensions, it'll be in the xy coordinate plane, and in 3 dimensions, it'd just be out here in space. So maybe it does something like this, all right? And so it traces out this path, but in a particular direction. So if we're looking at something like this, we can see that we might have something that comes along and then does something like this, where it's starting here, and it's ending here, and it's traveling in this direction. So the direction that the arrows go is called the orientation of the parametric equation. So it's producing a curve. This curve is not a function, does not pass the vertical line test, but it does relate the x and y coordinate systems. I can superimpose this on an xy plane, and it would tell me when it reaches a particular location, with the when being the t value, which is the independent variable for both x and y. So x depends on t and y depends on t. This path that we have is called the orientation, and it gives us both the where and the when. Now, how do we plot these points? We can create what's called a Txy table in order to plot points so that we can figure out where they are. Now notice t does not show up in the graph of the curve, because this, of course, is just the ordinary xy coordinate system, where that's the x-axis and that's the y-axis, and there is no t-axis. But I know when it reaches this particular location by knowing what the value of t is that results in that coordinate for x and that coordinate for y. So that way I know when it reaches that particular location. So because t doesn't actually show up in the actual graph, it's often called, like I said, a dummy variable. So typically when we're preparing these, we'll prepare an x and a y column and a t column. And the t column is generally listed first because x depends on t and y depends on t. And once we have the t values, we'll compute the x values and the y values, and then the x, y values give us the coordinate. T gives us when it arrives there, and the x, y gives us where it is at that point in time. And we can do the same thing for the parameter theta, which would give us, it reaches a certain location at a certain angle. So the angle is when it reaches that location as opposed to time. We could also, in fact, have parametric equations based on both t and theta. We're not going to get that complicated, but you can do such a thing. All right, now what does this graph right here represent? Well, this is actually the movement of the Earth's orbit around the sun in one particular year. So you'll see that there's a point here labeled F2. This is a focus point. Now the Earth travels around the sun in an elliptical orbit. It is not circular. I know a lot of people draw it as circular, but it's not a circle, it's an ellipse. And it turns out that there are 2 focus points for an ellipse. You should remember this from your study of conic sections and rectangular coordinates. We have one focus point here, and the sun is at another focus point. So we have 2 focus points inside of an ellipse, and then we've got the major axis here, and we've got the minor axis here. And so when we're looking at this particular picture here, we can see that we could actually superimpose coordinate axes over this graph so that we could have actually, if I can draw it without messing up, the x and y coordinate system. So here's x and here's y. And t doesn't actually show up on the xy system, but it tells me when do I reach that particular point in the orbit. So in fact, as the Earth moves around the sun, when do I reach this position in the elliptical orbit? The when is the t value, and the xy is the where value. So this basically allows us to assign ordered pairs to the position for a particular value of t, representing the time it takes in the calendar year to reach that point in the orbit. Okay, so when we look at these, this also, of course, is going to represent an orientation. I need to put arrows on it to show the orientation. And because of the way that time moves, the orientation is going to go this way from January to April to July, and then back around to October, and then back again to the beginning of the year. So the orientation is that we're moving around the sun in a counterclockwise elliptical orbit. All right, and as we're looking at this, each single point corresponds to our position in the orbit at a particular time in the year. So it represents position as a function of time. All right, so let's define the parametric equations. We've defined a parameter. The parameter is an independent variable, and we find that the x position and the y position depend upon the parameter. So x and y depend on the parameter. If we're in 3 dimensions, x, y, and z depend on the parameter. A parametric equation is just a curve. Now we're talking about the plane because we're going to focus on 2D, but in fact, this can be extended into 3D, even 4D, and so on. So a curve in the plane can be represented parametrically, and these representations are not unique. Now, this is something that is new. So in other words, the way that you write down the equation to generate a particular path is not unique. There might be infinitely many ways of writing down a parametric equation that generates the same path. And in fact, there are always infinitely many different ways. The equations that are used to define the curve that produce that curving pattern that you see coming around over here, where you're starting up here and you're ending here, and the orientation is following this direction right here. Those equations that are used to produce the curve are called parametric equations. And if x and y are continuous functions of t, remember they are functions of t, over an interval I, then the equations x of t and y of t are called the parametric equations, and t is the parameter for those equations. So the set of points that it generates, and again, this is generated out of the Txy plot that you do right here. All those ordered pairs that are produced while you're doing that are the graph of the parametric equations, and they will produce that curve. So when we're looking at this, the graph of the parametric equations is called a parametric curve, and sometimes called a plane curve if it's in 2D. Now, if it's in 3D, it's not a plane curve. When we write plane, we mean in a flat 2-dimensional surface. That's what we mean by plane. So a parametric curve in 2D is also called a plane curve. So what are the steps to graphing a parametric curve by hand? Well, first, create a Txy table. I know we're going back to the very first way we ever learned to plot things. We're plotting points. So we're going to choose values, and then we're going to compute x of t and y of t, and that will give us a coordinate. Now, the first value of t will give us the starting place, and the last value of t will give us the ending place. So we'll be able to label begin, end, or start, end, something like that. Now, we always want to start with t because it's the independent variable. When we're looking at this, notice again that the t will not show up on the graph, only x and y show up on the graph, but don't forget to draw arrows on the graph to indicate the orientation of the graph. It is different if it's traced backwards than if it's traced forwards, because it's reaching that point at a different point in time. So we always want to graph from the lowest parameter value to the highest parameter value, which means that we have to be given an interval over which to apply the parameter. And typically we are given a closed interval over which the parameter will apply. Now there are occasions, and we may see one or two, where the orientation of the parametric equation makes no sense at all. In fact, it jumps around all over the graph. It does produce a graph, a curve, probably not a function, but the way that it produces the graph is by flip-flopping back and forth and bouncing around all over the place. It doesn't graph in one smooth direction, one curved direction. In that case, it would be impossible to have arrows because it's jumping around. And you can see this quite often in trig functions because the trig values cause it to leap around from one place to another. So that can happen. Now you can use a graphing calculator like a Txy or 84 in order to graph these, or you can use an online graphing utility like Desmos, which is free. Desmos is, of course, easier to use. I will go through and talk about how to do both. So let's first talk about how to use a graphing calculator like the Txy or 84. This is the 84 that I have right here. This is a link to TI graphing calculator models. This is the full link right here. If you want to go to this link, you can look for the particular model that you have. And out there on TI's website, they have different subject-specific topics, and they have videos that go with how to use that particular graphing calculator to do different things. And so you would go out there and find out how to graph parametric equations on the particular model that you've got. Right? Now, if we're going to do this on Desmos, which is what we're going to learn quite often, my advice is to watch this 30-second video on how to produce parametric equations. So it's only 30 seconds long. It's not a big part of your life. Let's just go ahead and take the time, pause the video, go watch it, and come back. Okay, so hopefully you've done that. There is another video that covers how to deal with the orientation separately. So this is a little bit more involved. It's mostly the first about 5 to 11 minutes that's the most important. And here's the link for it right here. It's on YouTube. It's called Desmos Investigation Number 3, Graphing Parametric Equations, and you can find this right here. We will go through these steps as we work through our examples here because you'll see me using the techniques. So, but again, these are just short videos to give you an overview of how to do parametric equations in Desmos. Now, unlike what he says in the video, he says that you can't get pi as one of the limits on the parameter, but that's not true. You simply type pi, and that will translate as pi. So you can ignore when he says that that's not correct. So let's take a look at what it looks like when you're producing one of these parametric equations in Desmos. I like to use Desmos because it's free, it produces great looking graphs, and it's simple for students to use. So when we're looking at this one, notice that we have two equations. We have an x equation, x equal cosine of t, and a y equation, y equals sine of t. And we're also given a closed interval over which t applies from 0 to 2 pi. So here are the steps that we need to go through in order to produce this graph. So go ahead and open up your browser, go to desmos.com, and let's start entering this. The first thing you want to do to enter a parametric equation is the parametric equation is entered as an ordered pair. And you use the parameter t. Whenever you use t in Desmos, it assumes you're talking about a parameter. T is reserved for parameters in Desmos. You give the x equation for the parametric equation first, cosine of t, and the y equation for the parametric equation second, sine of t. Then down below that, once you've used t up here and entered it in ordered pair form, it automatically knows that this is a parametric equation. And so it opens up for you a range for you to enter the values of t. Now, if t wasn't given values, then presumably it goes negative infinity to infinity. You might choose negative 10 to 10 or something like that, just to see part of the graph, get an idea of what it looks like. In this case, we were given a closed interval, 0 to 2 pi. So I enter 0 to 2 pi. Now remember, to get the 2 pi over here, I actually type in 2pi, and that will enter 2 pi on that limit. Okay, now that will produce the parametric equation, okay? When we do this, it will instantly draw the parametric equation. The problem It just produces the simple graph. It does not produce the orientation. So it's going to show us what cosine of t, sine of t looks like, but it's not going to give us the orientation. So let me demonstrate that for you now. So we're going to put in cosine of t, sine of t, and close the parameter. Notice that it defaults to 0 to 1. I want it to go 0 to 2 pi. So I enter 2 pi, and I don't have to hit enter. It just automatically converts pi to pi. And it graphs a circle, which is the graph, but it's not the orientation. So I need to know the orientation. So how do I get the orientation? This is what's in that second video. So the next thing you want to do is you want to click on this gear symbol that you see right here. So this gear symbol that's up here, when you click on it, it opens up a sort of submenu, and it has these 2 sheets of paper. You want to click on the 2 sheets of paper in order to copy what you already have. So we're going to click on the gear symbol, and then it opens up this submenu. We click on this, and notice that what it's done is it's duplicated it. Now I want to say that I'm done, so I click on done. Now, it's no good to have the graph in there twice. What I want to do is I want to graph the orientation. So what I want is a slider bar. So I'm going to create a slider bar by changing the variable from t to something else. The one that I typically use and that's commonly used is a. Now, it could be something other than a, but typically we use a. So I have sine or cosine of a, sine of a. Notice that it automatically, when I take out the t, it goes, oh, this is not a parametric equation. You want a slider bar. So then I click on add slider. When I get this down here, it automatically goes from -10 to 10. That's default. If I click somewhere inside the box, I can change the interval to match the interval for t, which is 0 to 2 pi. Now, you can leave the step blank, or you can enter pi divided by 60, which is a good one. All right. Now, this is currently on the value a equal 1. All right. So let's come over here, and we've clicked on the slider bar. And then what we want to click on next is this double arrow. So there's an arrow pointing in each direction that we'll see down here. So when we point on that arrow, what's going to happen is it's going to pop up a submenu, which gives us options. So let's talk about what those submenus are. So over here, right here, you can see there's that double-sided arrow. So I click on it, it opens up a submenu. Now, this one means that it's going to graph it forwards and backwards. We don't want that. We don't want it graphing backwards. We want to know what the orientation of the curve is. So we only want to go forwards. The double arrows that you see right here, it just keeps going forward, 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 forever and ever and ever. And this one is going to go forward one time and stop. And this goes forward forever and ever and ever as well, I think. Let's see, what does this do? Repeats in one direction. This plays once, and this will play indefinitely. All right, so there's not a lot of difference between these two right here. I want it to play one time only. I want to see what the orientation is. I want to know where it starts, where it stops, and what the orientation is. So I want to trace the ball as it moves around. Now, if it's going too fast, you can use these symbols down here to slow it down. So this double less than will slow it down and make it go slower, and the double greater than will make it move faster. So we're going to click on it and make it go a little bit slower. So we're going to slow it down to about 0.75. Right, then click off of that. Always drag the slider bar back to the beginning. So when I'm looking at this particular graph and I want to know where it starts and where it stops, and I'm going to make it larger so we can see, it's starting on the x-axis at 1, 0. So this is the start place. So we want to pull the slider bar all the way to the left so that we're starting at the beginning of our interval. And then when we want to press the play button. So when I press the play button, you can see the ball moving around in a counterclockwise fashion, and it stops on 1, 0. So it goes around the circle one time and it stops on 1, 0. So to indicate the orientation, I need to label the point 1, 0, start, stop, and then draw arrows in a counterclockwise fashion around this particular graph. Right? So let's now start some practice. So we want to actually start practicing what we've been talking about. So if you have a graphing calculator, grab your graphing calculator and let's make sure you're in the right mode. So I'm going to go through how to use both the graphing calculator and Desmos. We will use Desmos most of the time in my class, but if you have a graphing calculator and you don't have the computer or Wi-Fi handy, then you can use the graphing calculator. So when you turn your graphing calculator on, up here in the top row, there's a button in the middle labeled mode. So you want to click on mode, and then you're going to see a screen that looks something like this one to the left. And you want to make sure in the fourth line that it has highlighted the PAR for parametric. So this is function parametric polar sequences. So we want parametric to be highlighted. So we're going to come down to parametric and then press enter on it, and that will highlight it. So use your cursor to get over top of the PAR and then hit enter. And now you'll be in parametric mode. Now go to the Y equals button. So remember, the Y equals button is to the far left underneath the screen. And when you click on that, you'll see that you have plot 1, plot 2, plot 3 across the top. And then you'll have x sub 1 of t, y sub 1 of t, x sub 2 of t, y sub 2 of t. These are different parametric equations. So it will list, I don't know, maybe up to 6 or 7 different pairs of parametric equations. So x of t would be the x value of t. So we could put in cosine of t there if we want to graph. So if you want to do that, you can enter that now. So you hit the cosine and then hit the variable button. When you're in parametric mode, the variable will not be x, it will become t. So when you're looking at that variable button, which is right underneath mode, it says x, t, theta, n. So it uses x for the variable in function mode, t for the variable in parametric, theta for the variable in polar, and n for the variable in sequences. So when we're looking at this, sequences and series. So when we're looking at this, I can put cosine of t here, and then I would want to put sine of t into the next one. Now, in order to see what the graph looks like, of course, you want to go ahead and produce the graph. Now, it's going to graph anything where the equal sign is highlighted. So if you have equations down here, but you don't want them to graph, use your cursor to get on top of the equals and hit enter. And it will take it off the pair of them. You don't have to change each individual one. Now, before we get to plotting, though, do you see this diagonal slash bar? So that just means it's going to connect it basically with a line as best it can and make it smooth. We want to see the orientation, and the best way to see the orientation is to graph the line, but also to see that dot moving around the circle. So this looks sort of like an old-fashioned key, which is a hyphen and then an O, or a hyphen and a 0. So you want to move your cursor to the far left until it's sitting on top of the diagonal slash, and then you want to hit enter repeatedly until you see that hyphen O. And when you see the hyphen O, then you'll stop right there, right? So once you can see the symbol right here is the hyphen O, then you know you have it set to plot showing the orientation, all right? So once you get the orientation in there and you've got cosine of t, sine of t, then you want to plot it, all right? So in the window, you have to set the parameters for t. So the next thing you want to hit is the window button, which is the second button underneath the actual window. So when you come over there, default is usually t going from -10 to 10. That's not what ours is. Ours is from 0 to 2 pi. So we want to change t minimum to 0 and t max to 2 pi. Remember, pi is the second above the caret symbol. Now, we don't have a choice about the t-step on a graphing calculator. You have to enter it in. So a good t-step is pi divided by 60. It's not too small that it really slows it down, but it's not so big that you don't get enough values. So it's a good value to use. So for t-step, you want to get down to t-step and you want to put in pi divided by 60. And it comes out to be that 0.0523, blah, blah, blah. All right, so I generally leave it on that. Now, I don't know what my x-min, x-max need to be or my y-min, y-max. I know what my t interval is, and I want to allow the calculator to compute the best values for x-min, x-max, y-min, y-max. So I use something called zoom fit. So when I look at zoom fit, I should talk about this first. What I was saying earlier about the t-step, if you do a t-step of 1, it produces a jagged, it's not small enough, right? You're not getting enough points to graph a smooth curve. And then a graph of t-step of 0.5 gives you a much smoother curve. The one that we have, which is 0.05, is going to give an even smoother curve. So when you choose a value of t-step that's too large, you get a sort of a connect the dots sort of picture. Okay, so let's now talk about zoom fit, which is on the zoom menu, which is the middle button underneath the window. So once we're in the window menu and we've set t-min, t-max, and t-step, then click on zoom in the center and then hit the 0, that's zoom fit. Now in the upper right-hand side, you'll see dots kind of going down and down and down, and it's thinking about the best possible X window and the best possible Y window for the values of the parameter between 0 and 2 pi. And it produces this picture right here, which we know is not correct because we've already done this in Desmos and we know it's a circle. And this does not look like a circle. What's happening? Well, the screen is not square on a graphing calculator, at least a TI graphing calculator, until they got to the TI Inspire where they finally squared it up. So in order to get it to have the same distance on the x-axis as on the y-axis, after hitting zoom fit, then hit zoom square. So hit zoom again, and then choice number 5 is zoom square. So now it's going to produce the full graph, and it's going to give us a pretty good circle, which you'll see right here. And when we do zoom square, it makes the distance on the x-axis and the distance on the y-axis the same, all right? Notice when you do that it does in fact show that little circle moving all the way around the picture. So you don't just get the circle, you actually see the circle moving all the way around and stopping back here. So you get the orientation from the key. Now, if you're not paying attention, you'll have to get it to graph again so you can see it again. All right, so this is basically what we're doing. We're getting the orientation where it's both starting and stopping at 1, 0, traveling in a counterclockwise circular motion and coming back to where it started. All right, let's take a look at the next example, which is example 3, based on x equals t squared minus 4 and y equal t divided by 2 for t between -2 and 3, using a TI-84 again. So now I'm going to put these into the second pair of parametric equations. So I highlight the equal sign in the first pair and hit enter to turn that graph off. And then I enter t squared minus 4 for x sub 2 of t. And then for y sub 2 of t, I enter t divided by 2. Then I go to the window key. I enter -2 for the minimum, 3 for the maximum. I leave mine at pi divided by 60. It's a pretty good value, even if it's not a trig related function. I don't want to do the x min, x max, y min, y max. I'll let the calculator figure out what that is. Hit zoom fit. After you hit zoom fit, hit zoom square. And when you're done, you're going to watch it trace out this curve that you see right here. Now, how can we know where it's starting and stopping in a static picture? Well, I can take the smallest t value, which is -2, and put it into each of the equations for x and y. -2 squared is 4, minus 4 gives me 0, all right? And then t divided by 2 is going to give me -1. So it's starting at 0, -1, which means it's starting down here. And then if I plug in 3, I'm going to get 9 minus 4, which is 5, over 3/2, which is this point up here. So it's traveling in this direction right here from the lower part of the parabola, sideways parabola, from the lower arm at 0, -1, traveling in this direction, which is clockwise, and ending up there at 5, 3/2. Right? Now let's go ahead and look at the same one using Desmos. So when we're doing Desmos, again, what we want to do is we want to enter the two parametric equations in ordered pair form. So we have t squared minus 4, t divided by 2. We set the parameter to go from -2 to 3. We click on the gear symbol. We get a copy of the page. So we copy the page, then we change the variables to A. We click on add slider, and we click in the slider and set the slider to go from -2 to 3. Then we click on this symbol. We want it to trace it one time only and stop. And I believe that I did not put in. Okay, so let's go ahead and graph this one. T squared minus 4. So this would give me t squared minus 4. And then I believe the next one was t divided by 2. And it's going from -2 to 3. And then I need to do the same thing in here because I've got to change that or it's still going to be going on the wrong one. So this becomes a squared minus 4. And then it becomes a divided by 2. And I also need to change my slider value to go from -2 up to 3. All right. Now I want to click off of there. Then I want to grab my slider, move it all the way back to the beginning. I want to kind of scroll out a little bit so I can see the whole thing. And then when I click on the play, you'll be able to watch it as it traces out the orientation of this parametric curve from beginning to end. Let's take a look at the next one, which is sine of t, y equals sine of t squared. So I put this one in the third pair of parametric equations. This one goes for t between -10 and 10. I kept t steps still at pi divided by 60, then hit zoom fit, then hit zoom square, and you get this glorious mess that you see right here. It's definitely not a function, all right? In fact, on a graphing calculator, because of the resolution, it's kind of difficult really to see what the pattern is. So I believe for example 6, we do the same thing, but using Desmos. So when you're looking at this one, you'll see we've got sine of t squared, t between -10 and 10. Then we copy that, we replace t with a, we create a slider bar, and you can see that it's graphing. Now, let's go ahead and graph this one, and then we're going to trace it as it graphs out. It's going to be kind of all over the place. So this was the parametric equation sine of t squared. Right, so I've got sine of t squared. All right. So this is going to be sine of A and sine of A squared. All right. And then we want to click in here and we want to change this to go from -10 up here to 10. And we'll leave the step blank. All right. Now let's go ahead and change this dot to a different color so it's easier to find. So we'll make it blue, and I'm going to make it much larger so that we can trace it a little bit more easily so we can see that there. So let's go ahead and, oh, I didn't change this up here. So this needs to go from -10 to 10. And now we can see that trace over here. So we're going to blow up the picture so that it's easier to see the pattern. So now you can see the pattern pretty well. You can tell that it's tracing all this crazy kind of stuff. Let's go ahead and pull the slider bar back down to 0 and let it play one time. And we're going to slow it down so that it goes a little bit slower. So we're going to go 0.5 instead of the regular. Now we want to click on play. Notice where it's starting. I pulled the slider bar all the way back, so it's starting right here. And now when I click play, keep your eye on the blue dot. Holy smokes, it's all over the place, right? And then it slowly, and then it graphs. It's pretty crazy, right? And it ends up right here, all right? That's where it ends. So it would be very difficult to put all the arrows on here for the orientation, but on Desmos, you can play it slower and slower so that you can see more slowly or more clearly what the orientation of this parametric curve is. Now, how do we put in a parameter if there is no parameter in the equation? In other words, how do we turn something into a parametric equation? So how can we create a parameter where we don't have one? Well, the easiest thing to do is simply to let either x or y become t and to rewrite the equations in terms of t. And that will give you a parameterization, all right? So if you let x equal t, then y gets written in terms of t since it was originally in terms of x, and you have two equations, x equal t and y equals some function of t. Parameterizations are not unique. There's almost always infinitely many ways to parameterize the exact same curve, so they're not unique. But there is usually an obvious choice or a simpler way to parameterize. Let's take a look now at example number 7, where we're going to parameterize the parabola y equal x minus 2 quantity squared plus 1, first by choosing x to be t, and then by choosing x minus 2 to equal t. So we're going to do both of these parameterizations. We'll see it gives us a different set of parametric equations for each one. So let's start with choice number 1. In choice number 1, we're going to let x equal t, and that means that we can rewrite our second equation as t minus 2 squared plus 1. So this makes both x and y functions of t. So now we have a parametric set of equations. I know that sounds almost too easy, but that is really all you have to do. That makes it very, very simple. Now, this gives us this set of parametric equations. What would happen if instead I had chosen what's in parentheses, x minus 2, to be the parameter t? Then I would have, in this case, since x minus 2 is equal to t, then x as a function of t becomes t plus 2. And then I can rewrite y as a function of t by rewriting this equation that you see up there, which would become t squared plus 1. So this is a different set of parametric equations than the ones I have above. But if you put both of these into Desmos, you're going to get exactly the same curve. It produces, again, an upward opening parabola with a vertex at 2, 1. So both of these produce the same curve. Different representations, different parametric representations, producing the same curve with the same orientation. Now let's talk about how to eliminate the parameter and to rewrite a parametric equation in terms of a single equation relating only x and y. Now we're assuming, of course, that we're dealing with plane curves. In other words, we're in 2 dimensions only, x and y, no z. This process can help us identify what the type of curve we have. Is it a circle, an ellipse, a hyperbola, some other known shape? There are lots of known shapes. But it does remove the orientation from the curve and it hides the restrictions on the domain of the parameter due to the restrictions on t. So there are some disadvantages to doing this. We don't get the orientation anymore, and we don't have the restrictions on the curve based on the restrictions of t. So you have to kind of remember that that is going to produce restrictions on the value. Now, the simplest way to eliminate the parameter t and to rewrite it in a single equation in terms of x and y is to solve either x of t for t or y of t for t. Solve one of those equations for t and then substitute into the other parametric equation and solve for y if you can. You can't always do it. Remember that parametric equations are good for equations that cannot be written explicitly in terms of y. So sometimes you can't. All right, when a trig function is often involved, we will often solve for the trig function in each of the parametric equations and then use a Pythagorean identity in order to eliminate the parameter. So let's take a look at this next example that we have down here and see how we can eliminate the parameter to find a rectangular equation for the plane curve. And by rectangular equation, what we mean is a Cartesian equation or an equation in terms of x and y only. So rectangular coordinate system is what that refers to. So our parametric equations are x of t equal t squared and y of t equal to 2t plus 3. T has restrictions that it goes between -3 and 3. So when I'm looking at this particular one, I'm going to have the value. I'm going to look at this. Note that this is going to begin at the ordered pair when t equals -3, which is going to be at the ordered pair 9. Let's see, that would be -6 plus 3 is -3. 9, -3, and it will end when t is equal to 3, which would be at the ordered pair 9, 6 plus 3 would give me 9. So it ends up there. So whatever this curve looks like, this is where it starts and this is where it stops. So this is the orientation part of it. And now what we want to do is we want to take our 2 equations, x equal t squared and y equal 2t plus 3, and we want to solve one for t. Now, which one do you want to solve? Yes, this has already got t isolated, but it's t squared. And to solve for t, you get a plus or minus, and that is nasty when trying to plug in. So even though it is more complicated on the y equation, you should take the y equation, subtract 3 from both sides, and then divide by 2 to solve for t. So you get y minus 3 divided by 2. Now I've used the y equation, so I want to take this expression and substitute it in the other parametric equation that I haven't used yet. So I'm going to sub into the other one. So I get x equals y minus 3 over 2 quantity squared. And then I can go ahead and multiply out this fraction twice. So I have y minus 3 quantity squared divided by 4 equal to x. And I can move the 4 to the other side, and then I can get y minus 3 quantity squared equal 4x, right? Which of course is the equation for a sideways opening parabola, right? Now, if I want to solve this exclusively for y, I would now need to take the square root of both sides, and that would give me y minus 3 equal plus or minus the square root of 4x. Now the square root of 4 would give me 2, so this would give me y minus 3 equal plus or minus 2 square roots of x, and then when I solve for y, I get 3 plus or minus 2 square roots of x, right? Which would be an explicit formula for y. This would be an implicit equation for y, and this is an explicit equation for y. To my mind, the implicit one is better because it reveals the underlying structure. This is a sideways opening parabola, right? So now what we want to do is take a look at the next example, which is example number 9. And what we're doing in example number 9 is a very similar thing, but this one involves trig functions. So we have x equal 5 cosine of t and y equal 2 sine of t. And t goes between 0 and 2 pi. So again, we can find where it begins and where it ends. So it's going to begin when t is equal to 0. And that means that the x value is going to be 5 times the cosine of 0. Cosine of 0 is 1, so we get 5. And the y value, again, we plug in 0 for t. Sine of 0 is 0, so the y value is 0. So it's starting at 5, 0, and then it's going to end when t equals 2 pi. But 2 pi is a multiple of 0, so it's basically going to come right back around to 5, 0. So whatever it's doing, it comes back to where it started, all right? And this is giving us sort of the orientation. We'd have to plot more points to know what the orientation is once we've eliminated the parameter, because we don't have any other way of telling. So in order to eliminate the parameter here, it's more helpful to isolate the trig function. So we're going to take our two equations, x equal 5 cosine of t, and we're going to rewrite this as cosine of t equals x divided by 5. Then we're going to do the same thing for the y equation, 2 sine of t, which is going to become sine of t equal to y divided by 2. Now, what equation in trigonometry do we know that relates sine and cosine? Well, there are several of them, but there's one trig identity, which is that sine squared plus cosine squared equals 1. So the next thing that we're going to do is we're going to reproduce that one. So we have sine squared of t plus cosine squared of t has to equal 1. That's a Pythagorean identity, so we know that that's what it's got to be. So when we're looking at that, we're going to make the substitution that y over 2 is going to replace sine. So we have y over 2 squared plus x over 5 quantity squared equal to 1. All right. And the next thing that we can do, of course, is multiply this out. You might prefer to have the x term written first. This is basically going to give you x squared over 25 plus y squared over 4 equal 1, which is the equation of an ellipse. So when you're looking at this one, you'll see that it is an ellipse when you graph it on Desmos, and you can see that it starts here at 5, 0, and it ends at 5, 0, and it traces this ellipse in a counterclockwise orientation. Now, you wouldn't know the counterclockwise orientation unless you graphed it as a parametric. Graphing this just gives you the black outline of the ellipse, not the orientation. Now let's talk about a few of our known parameterizations for which we know what the graph is going to look like. If you have a parametric equation, which is x equal to some constant value plus a times cosine of bt, and you have a similar equation, but for y equal to some constant y naught plus a sine of bt, then you're going to get a circle. All right, so this is going to produce a circular equation. It'll trace it out counterclockwise, provided that b is positive, and it'll go clockwise when b is negative. So in one, it goes in the positive direction, which is counterclockwise, and when b is negative, it goes in the negative direction, which is clockwise. The circle will be rotated around 2 pi divided by the magnitude of b. So if b is 2, then this would be 2 pi divided by 2, which would be, it'll go around pi times, so about 3.14. So 3 full revolutions of the circle plus a little bit more. The magnitude of b becomes the angular velocity, that change in the angle with respect to time, and a is the radius of the circle, right? Now, x naught and y naught can, of course, be 0, in which case it becomes very similar to the one we did up above. Now, how is it different from the one that we did just a minute ago, right? So when we're looking at this one, we can see that we had different constants on the front of the trig function. So we didn't have a in both cases. We had an a on one and some other value on the other, c or something like that, and it produced an ellipse. There's also something called a cycloid, and cycloids come up a great deal when we're talking about physics types of applications. There are lots of things that rotate, and if you take, for example, a bicycle wheel and you put a straw at one point on the spoke, and then you trace out, or a marker even is better, and you trace out as the wheel turns, it traces out this sort of shape right here, which is called a cycloid. So the cycloid often looks like this, something like that, or it could go the other way as well. It could be turned concave up. So these are cycloids, and they have a known pattern to their equation, x equal a t minus sine of t, y equal a 1 minus cosine of t. And when you do this, you're going to get a very cycloid shape. So it's generated by a circle or a bicycle wheel of radius a going along the edge. They often have cusps in them, which of course are those pointy parts in the graph. Now this should remind you of the toy that you may have played with when you were growing up, the spirograph art set that basically gives you a set of circular wheels, and you can put different kinds of wheels on the inside, put your pen through the hole, and then go around and around the inside of that ring, and it will draw different kinds of shapes. And you do it with different colors, you get different kinds of patterns. That's basically what you're doing, is producing cycloids. So that's basically the way that a spirograph works. Now, this is when it's not traveling along a straight road, so it's not giving you that shape that we saw up here, which looks more like this shape. But when it's going around a circle, it will give you one of the shapes that you see here on the spirograph box. So it can give you all kinds of different shapes. So here's an example of one that produces this shape that you see here in orange, and it's produced, of course, by tracing this around on this particular circle. So here's the outer circle, which would be like the spirograph ring, and here's the inner circle, and you put your pen through that circle right there, and you pull that inner circle around the outer circle, and it's tracing out this shape that you see here in orange, right? And that is basically called a hypocycloid, right? And the general parametric equation for a hypocycloid is right here. Now, I am not going to expect my students to know the general equation for even a circle or a cycloid or a hypocycloid. They get quite complicated, but they do produce some pretty spectacular and pretty beautiful graphs. So they're kind of fun to play with, but I would not expect you to memorize these formulas. In this equation right here, the radius of the larger circle is a, and the radius of the smaller circle is b. And so the center of the wheel, the inside one, is traveling around a circle of radius a minus b. So when we're looking up here at this, we have this radius of a, which is on the outside, which I could draw right here. This is a, and this inner one is b. And so it's going around on a radius of a minus b, all right? So did I draw that right? No, I did not. I'm looking at this right here. This radius is b. There we go. And now we've got a minus b, all right? It's going around there. Okay. So what are some other things that we get when we look at a hypocycloid? The ratio of a over b is related to the number of cusps on it. These are well-studied shapes. They're well known. They have applications in various places. Plus, they're just super fun to play with and draw. The ratio of A over B, if it's a rational number, remember rational means ratio of two integers, then there will be a finite number of cusps. And the hypocycloid will return to the starting point and retrace exactly the same path over and over and over again. Now, if the ratio of A divided by B is not a rational number, it's not the ratio of two integers, all right? It's an irrational number, then there will be an infinite number of cusps, and it's what we call a space-filling curve, all right, where it will fill up the space. So let's take a look at these examples that are drawn down below. So when the ratio of A over B is 3, we see that there are 3 cusps in the hypocycloid, and it will just continue to trace out the same pattern over and over and over again if you allow the angle for t to get larger and larger. And then if A over B, the ratio is 4, you see that there are 4 cusps, and again, it will trace the same path over and over and over again. When there are 5, when it comes out to be 5, there's 1, 2, 3, 4, 5 cusps, and again, it will trace the same one over and over again. But that also applies to other kinds of rational numbers like 5/3, which is not a whole value, but it will relate to the number of cusps that we see here. And then you will see that it does trace out this shape over and over again as we allow t to go to infinity. 7/3, we get this right here. We do have 1, 2, 3, 4, 5, 6, 7 cusps, and it's crossing itself on the inside. And then 8/3, of course, we've got the 8 cusps. Now, what happens when it's an irrational number, the ratio of A over B, something like pi or the square root of 2, is that it becomes what's called a space-filling curve. Now, I stopped it at a certain point on these so you could see the pattern, partly because they're beautiful, and partly because otherwise it's just a big solid blue dot, which doesn't help much. So this is stopping at some particular part on the way through. This one is not going to fill in the inner space, but it's going to fill in this outer space until it's a solid blue ring, all right, called an annulus. If I allowed t to go to infinity, it's going to fill up those spaces so they look solid. So this one is a space-filling hypocycloid. I set A to be 2 pi and B to be 2. And I put this equation into Desmos. You can see it right here. And I created a copy and added a slider bar. And then I allowed the slider to go from -1,000 to 1,000. So I'm taking a really large range because this is a space-filling curve. And because the ratio of A over B is an irrational number, it will eventually fill that space and make it solid. Now, what I see so far is I've stopped it. It's gone from -1,000 up to a little more than 33. And you can see that there's still some empty spaces in here, right? I mean, there's still some white space in that curve. If I allow it to go all the way up to 1,000, though, it just produces a solid black annulus. This is called an annulus, otherwise known as a ring shape. Annuli for plural. So annulus is singular. It's basically a ring. It's a donut, basically. So when you get the donut shape, we call it an annulus, and this is what it would look like. And this is what we mean by space filling. And if you want to play with it, I have a link right here that you can use if you have the access to my notes. Looking at this one, we have example 11, which is graphing a non-space filling hypocycloid where A is 16 and B is 3. So the ratio is 16 over 3. So we know that it should repeat the pattern. Now, sometimes Desmos has a little trouble with it, but we can see right here that it's basically producing this shape right here. And it will repeat this shape over and over again. It's not going to fill in the spaces. It's not going to become a solid black annulus or anything like that, or a solid dot. Some of them become completely solid circles, and some of them become annuli that are filled in. This one will not. It will repeat the pattern as you keep going. Now, we've had some examples of how to use parametric equations, what they look like. where they might come up, looking at bicycle wheels and rotating around a circle, all these kinds of things that come up in physics. But we haven't actually done any calculus with it. Everything we've done so far has been algebraic. In the next section, we want to take a look at doing calculus with parametric equations. So obviously that means that we'll want to find the slope of the tangent line or the derivative. We'll want to find the equation of the tangent line. All right, so I hope that you will join me for the next video where we take parametric equations into calculus.